Hello, this is the third of the lectures on numerical methods. The last one, we're going to be covering a different topic from the previous two, and this topic will be solving equations. And we're going to learn two different methods for solving equations, as is shown on the slide, the bisection method and the Newton-Raphson method. So what is this all about? Well, in the past, you've learned how to solve certain equations. So for example, here you see a quadratic equation, and the objective here is to find all the values of x such that this equation would be true. And in this particular case, there's two values you should know very well. You can use the quadratic formula. -3 and 1 are the two solutions of this equation. Of course, there's other equations. Sometimes there might be only one solution. Here's another equation. E to the x equals 1. You can take the natural log. You know the only solution is x equals 0. Another example, sine of x equals 0. There's actually infinitely many solutions of this equation. Of course, x equals 0 is one possibility, but x could actually be any multiple of pi. Remember that we're dealing with radians when we use the trig function. So in radians, the solutions of sine x equals 0 are all the integer multiples of pi. And so these are some examples of equations where you can find a formula for the exact solutions. But in general, when we're dealing with real-world problems, oftentimes we're faced with an equation where we have no way of finding the exact solution, or no way of finding an analytical formula for the exact solution. And so what we want to talk about is how can we estimate the solutions of such equations. And we consider very general cases here. So consider the case, the general function of general function of x equals 0. So for example, in the first equation here, the f of x would be sine of x, and this one it would be e to the x minus 1. We move everything to one side, or this quadratic polynomial in the top one. And so we want to find a way in general of finding the solutions of this type of equation. We assume we know the function f. We want to find where it's equal to 0, the values of x for which it's equal to 0. And there are two methods that we'll study. There are other methods beyond these, but we're going to look at two. The first one is really the most simple. And if you were to think of a way of solving equations like this, maybe it would be what would pop into your head. And it's called the bisection method, also sometimes called the midpoint method. And here's the idea. So the function that you want to find the 0 of, so the function f has to be a continuous function. And the first step, the input to the algorithm, if you like, is you have to find two values of x where the function has opposite signs. So for example, we have this graph of a function here, and at a the function is positive, and at b the function is negative. So if it's positive on one side and negative on the other, you know it has to go through 0 somewhere in between because it's continuous. And so the idea then is fairly simple. As the name bisection suggests, you then bisect this interval from a to b. You find the midpoint of the interval, work out the m, which is halfway between a and b. So the formula is m is 1/2 a plus b, the average of a and b. And then you either take the interval on the left or the interval on the right, and whichever one has the 0 in it, based on the sign of m. So you replace either a or b with m, so that in such a way so that f of a and f of b still have opposite signs. So in the case shown here, you would replace a with m, and so that still at a, f is positive, and at b, f is negative. And then you just repeat this. So now you have a new a and b. You find the midpoint. You replace either a or b so that you still have a 0 in between a and b. And you just continue until you reach the desired accuracy. And it's very easy to see how accurate it is, because you know that there's got to be a 0 somewhere in your interval here from a to b. And so you just keep squeezing that interval until it's as small as you want it to be. And so I'm going to go through an example. So we're going to find a solution of x cubed equals 2. And so you may know this x as 2 to the 1/3. All right, and I'll do this by hand. So in this case, the f of x we want to use Okay, so we want to find the solution of x cubed equals 2. And so in order to translate that into an equation that's f of x equals 0, we just subtract 2. So you get x cubed minus 2 equals 0. And so the f of x that we'll use will be x cubed minus 2. Okay, and well, you can look at the graph of this function, figure out how you find a and b. There's no prescribed way to find a and b. You have to guess at one number that where the function takes one sign, and then find another number where it takes the opposite sign. But in this case, it's not so hard. So for example, take f of 1. So that's going to be 1 cubed minus 2 is negative 1. And so we could maybe take a equal 1. Take f of 2. That's going to be 2 cubed minus 2. So that's 8 minus 2, 6. And so these have opposite signs. There has to be a 0 for this function somewhere in between 1 and 2. And so we take a equal 1, b equals 2. And now we just repeat the steps in the algorithm. So the first step, we know that the 0 is in this interval from a to b, or 1 to 2 in this case. And so we have to calculate the midpoint of this interval, m, the average of the two endpoints, 1 plus 2 over 2. That's of course 1.5. And then you have to calculate the function f evaluated at this point, 1.5. So f evaluated at 1.5, 1.5 cubed minus 2. And I've worked this out in advance. It's 1.375. And so 1.375 is positive, and so it's going to replace the positive endpoint. That is the endpoint 1.5. The midpoint m is going to replace b, which is where the function was positive. And so we replace b by 1.5. And we move on to the next step. So in step 2, we know that the 0 has to be between 1 and 1.5. Here the interval be between 1 and 1.5. And we just repeat the same steps. So you first find the midpoint m. M is 1 plus 1.5 divided by 2. That's 1.25. Have to evaluate the function f at this point. And this will be 1.25 cubed minus 2. And 1.25 cubed minus 2 is negative 0.047. This is less than 0. And the function was less than 0 at the point 1. So we replace the left-hand endpoint, the a, by 1.25. And so place a 0.25. And so then step 3, we would know that the 0 has to be in the interval from 1.25, 1.5. You would find the midpoint. M is 1.375. 1.25 plus 1.5 divided by 2. The function evaluated at this midpoint is 1.375 cubed minus 2 is 0.6. And so we would replace the right-hand endpoint, 1.5, because that's where the function was positive, by 0.6. And so the next interval, 1.25 to 1.375. Okay, and I'm not going to do any more. I hope you get the idea. It's very simple. You just have to compute the midpoint in each step and then evaluate the function f and see whether it's positive or negative. Okay, so I have a bit of a graphical representation of this example we just did, just to drive the point home. So this is the same example we were just discussing. So the function is x cubed minus 2. And as I went over in the example, the two initial endpoints are a equal 1 and b equal 2. And here I have the graph of x cubed minus 2. A is 1 and b is 2. And the first step would be you find the midpoint. That's what we did. M is 1.5, halfway between a and b. And then you can see that the 0 occurs in between 1 and 1.5, so b changed to 1.5. Take the next midpoint, m equals 1.25. And see that you have to replace a by 1.25. And so these are the first two steps. And you can see this interval shrinks by 1/2 at each step. All right. So I'm going to do one more example with the bisection method, just to showing you that, in fact, you don't really have to manipulate the problem so that it's a function set equal to 0. It could be a function set equal to a different number. So in this case, we have sine of x equals 0.3. And the idea, when it's the right-hand side of some number besides 0.3, you just evaluate the function and see whether it's more or less than 0.3, and then change the endpoints accordingly. So just do a few steps of this, kind of demonstrate how it works. So the equation we want to solve is sine of x equals 0.3. And so this equation actually has more than one solution, like sine of 0 or sine of x equals 0 has more than one solution. But we'll find the positive one that's smallest, just to find you what this looks like. So we have the sine function. Its maximum value would be 1. And we want to find where it's 0.3, the smallest positive value of this. So the x we're looking for is the x right here. Right, and so the first step, you have to find the a and b that you start out with that surround 0.3. So sine of a should be less than 0.3, sine of b should be more than 0.3. And in this case, we can take a equals 0 and b equal 1, since sine of 0, of course, it's 0. Sine of 1, 0 is less than 0.3, just to point out. And sine of 1 is approximately 0.84. It is, of course, more than 0.3. So that means the sine function, since it's continuous, has to equal 0.3 somewhere in the interval from 0 to 1. And so the first step then, in the bisection method, we know that the solution of this equation has to be somewhere between 0 and 1. And so we find the midpoint. The midpoint here, of course, is 0.5. Between 0 and 1. Compute sine 0.5. And this is approximately 0.479. Greater than 0.3. And so we replace 1, which was the endpoint where it was greater than 0.3, by 0.5. So the new interval (0, 0.5). The solution of the equation has to occur somewhere between 0 and 0.5, and 1 is something like here. So we've just split this in half. I should have drawn this a bit bigger, but we split this in half. Now we know that the x is between 0 and 0.5. All right, and then I'll just do one more step here. So the step 2, we have that the the solution of the equation is between 0 and 0.5. We find the midpoint. Of course, it's 0.25. Compute sine of 0.25, which is approximately 0.247. less than 0.3. And so we're going to replace 0 by 0.25. And so the new interval 0.25 to 0.5. So we know that this x has to occur somewhere between 0.25 and 0.5. And of course we can continue on in the same way. I won't do any more, but it's very straightforward if you want to refine the estimate further. Okay, so this is the bisection method. Quite simple. It has some advantages and disadvantages. The advantages is that it's very simple and works for any continuous function. The function only has to be continuous, and then the bisection method will work. It's simple, as I said, number 2. And another advantage is that it's you can quantify the error exactly. So you start out with a given interval, and each time it is halved. And so you know the solution of the equation. Your error in finding the solution of the equation is multiplied by a half at each step. So you can tell exactly how accurate you've estimated it. The disadvantage is that it's quite slow to converge compared to other methods. So the second method we're going to look at is the Newton-Raphson method, I'm going to cover in a minute. And the bisection method is much slower than the Newton-Raphson method, as we'll demonstrate. And another disadvantage is that it relies on this continuity property where you know the function has to go through 0. So if it starts out on two sides of 0, it has to go through 0. And if it's a function of more than one variable, or maybe even a system of equations, there's not an obvious extension of this principle to that case. Whereas actually with the Newton-Raphson method, it can be extended to such cases. But if you only are finding a solution of a single equation with a single unknown x, then it's very flexible and simple. Okay, so now look at the other method of solving equations, which I mentioned at the beginning, the Newton-Raphson method. So the advantage of this really over the bisection method is that it's much faster. And I'll show we'll demonstrate that in a minute. So it's an iterative method, actually also like the bisection method. You start out kind of with an estimate of the solution, and then there's a formula that gives you a next estimate, and you just keep repeatedly, iteratively apply this formula. And the principle of the Newton-Raphson method is you start out with this given estimate, x0. So let's say we think x0 is approximately a solution of sine of x equals 0.3, the example we were looking at before. And then the idea is you find the tangent line to the graph at this point. So we have a tangent line. The slope is the derivative at that point, as we know. And then the next estimate is the point where this tangent line intersects the x-axis. So it's essentially you replace the function by the tangent line, and you find where that tangent line is 0, and that's the next estimate. And then it's iterative, so you just now replace x0 by x1 and go back to the beginning. So you find the tangent line to the graph at x1, and look where that intersects the x-axis, and that's the next estimate. You might call x2. Okay, so you can just repeatedly apply this as many times as you'd like. All right, and so we can find the general formula to go from x0 to x1. And this is based on the formula for the slope of the tangent line. So recall that the derivative of the function at the point x0 is the slope of the tangent line. And the slope of this tangent line, well, it goes from x1 to x0 and rises up from 0 to f of x0. And so the rise over the run is the slope, so f of x0 divided by x0 minus x1. That's the derivative at the point x0. And then you can solve this equation for x1. And that gives you the formula to go from x0 to x1. This is the formula for the Newton-Raphson method. So given initial guess, x0, you go to the next guess by following this tangent line method. All right, so I'm going to do it with the same example, apply the Newton-Raphson method to the same example we were looking at with the bisection method. And so the formula we want to solve, sine of x was 0.3. And so with the Newton-Raphson method, you do have to set it up into the form f of x equals 0. So we subtract 0.3 from both sides. Set it up in this form, and now it has the form f of x equals 0. And in order to apply the method, you have to take the derivative. So the derivative of this, we just need to know the derivative of sine, which is cosine. And then the formula for the Newton-Raphson method is x1 equals x0 minus f of x0 divided by the derivative of f at x0. And then we want to do it in this particular case, so we plug in the functions for f of x and f prime of x, the derivative of x. Have this sine of x naught minus 0.3 divided by cosine of x. And this is the formula that goes from x0 to the next estimate x1. And so we do this, we go from x0 to x1, and then you plug x1 back in for x0, and you just keep doing it. You do it iteratively. And this can give us an estimate. So I'm going to demonstrate how this works. So you can do it by hand. As I mentioned with the numerical integration techniques, this is really something that you want to do using a computer. You can do a few steps by hand, and you may have to do that on the test because we want to test that you understand the method. But to apply it in practice, you want to use a computer and program the computer. And there's many different ways to do this, but I'm going to demonstrate it today using Excel. So this is just a spreadsheet. You could use a different spreadsheet, but this is Microsoft Excel. And so let's show how you can apply the Newton-Raphson method to solve this problem. So we're going to, first of all, put in our initial guess that we're going to say. And so we'll start out with x0 equals, say, 0. Okay, and here I'm going to set this equal to the initial guess. And then here I'm going to write the formula for the iteration. And so the formula was its initial guess minus sine of the initial guess. Oh, sorry. Made a mistake. I want to use this one. The initial guess minus sine of this initial guess minus 0.3 divide by cosine of that initial guess. Okay, and so this is the first result, the first guess, so this would be x1. And then if we want to put it back in, well, if I drag this down, it's going to take this initial guess and put it in the first column here, and then calculate the formula using that x1. And so if I just drag this down, it will show us the iterations of the Newton-Raphson method. And you can see that actually in this case, it doesn't change after we've gotten to the second iteration here. So after this, or at least, oh, I guess the final decimal point there does change from 3 to 5. But it becomes very accurate even at the second iteration, and then the third iteration onward, it doesn't change up to the accuracy that's displayed here. And let's just check this by well, using Excel's function to find the exact sine inverse of 0.3. And so you can see this agrees with what we found using the Newton-Raphson method up to the number of decimal points that are displayed. And that's after only 2 iterations. So using the bisection method, we had nowhere near this amount of accuracy after 2 iterations. So here is a demonstration that the Newton-Raphson method is just much, much faster. The Newton-Raphson method, even though it has this advantage, it has some disadvantages as well, and that is that it can behave strangely, especially if you start near a point where the derivative is 0. So we divide by the derivative in the formula for the Newton-Raphson method. So you can see if the derivative is 0, there's going to be a problem. And even if you're near a point where the derivative is 0, there's going to be a problem. And so let's say, so the derivative is cosine in this case, and so let's make the initial guess something that's close to where cosine is 0, which is pi over 2, so 3.14596, approximately pi by 2. Okay, and so if we make the initial guess this, you can see that the method behaves quite differently. And it goes out actually to a very large number, and then it appears to stop there. So what has happened here? It is a bit mysterious. So the fact that it goes out, first of all, to this very large number has to do with the fact that the derivative, the cosine at this point, is very, very close to 0. And so that means the tangent line is very close to flat. And so if you think about where the tangent line will meet the x-axis, it goes very, very, very far out. And then it's maybe strange that it converges, or appears to converge, to this large number. Well, this just has to do with the fact that there's many solutions of this equation, sine of x equals 0.3. Let me actually go back and try to demonstrate this. Drawing it. All right, so here we have some axes. Let's say this is negative 0.3, and so the function sine of x minus 0.3 looks something like this. And actually, this is the point that we're trying to find, but there's other solutions of the equation. You know, for example, here, and actually infinitely many of them. And if we start out close to this point, which is pi over 2, where the derivative is 0, if we're very close to this point, slightly more, you can see that the tangent line is flat right at that point, or close to it, is very close to flat. And so if you look at where this tangent line is going to intersect the x-axis, it's very, very far out here. So the way I've drawn it, it's actually not as far, not in the thousands or tens of thousands like in the demonstration, but it will go out very far. And then it will, once it's gone out there, it will converge to a 0, which is close to that. So this example, we would start here, we would go to, start at this point, x0 perhaps, go to this point, x1, and then the iterations would converge to a point, the 0, the solution of the equation, which is close to this point, x1. So that's what's happened. And this is the unpredictable thing about the Newton-Raphson method. If there's more than one solution, you may not converge to the one you want. And if you start out close to a point where the derivative is close to 0, it may have very unpredictable behavior. It may become very large. Okay, go back to the slides. I want to do one more example using the Newton-Raphson method. So as I've been explaining, the Newton-Raphson method works well if you start out close to the solution you're looking for. It can be unpredictable, like in what I was just showing you. But it gets very accurate very quickly if you start close to the solution. And so here's an example that demonstrates that. So suppose we wanted to find a solution to the other example we used. We applied the bisection method to x cubed equals 2. That is the cube root of x. And say we want to find it to 20 decimal points. So using the bisection method, this would require probably at least 20 iterations, probably a bit more than 20 iterations. But using Newton-Raphson, well, we first of all derive the formula. So the function we want to use is x cubed minus 2. Gives us the cube root of 2 and it's 0. And so we take the derivative, that's 3x squared, and we can simplify that slightly. So the iteration formula for Newton-Raphson method is here. We apply this. We're starting with the initial guess, x dot equals 1. The first step will be 1 1/3. And then we can continue. And you can see the number of decimal points of accuracy, which are the black ones that aren't grayed out, increases, or about doubles at each iteration. Yeah, I should hide myself for a second. And so you can see already by the 5th iteration, we've maxed out the number of displayed accurate decimal points here. All right. So this is the Newton-Raphson method. One point to stress again is that you don't want to do more than a few iterations of this by hand. And so, for example, in this, what I've just done, you can use Excel in the method that I showed, or they demonstrated with cosine, in order to find these iterations rapidly up to the 6th iteration, and actually much, much higher if you wanted. But in general, this is a method that should be done in a computer that's programmed to do it iteratively. And because it has such a simple formula, it's quite easy to program computers to do this. Okay, well, that's the end of this lecture. Next time we'll be continuing to the next topic.